of the electric field. So this is dx over minus 2x has to be equal to dy over 2y. That means what we're saying is that when we draw electric field lines, we draw it in such a way that at each point the electric field itself is tangent to those lines. So this gives us what is this out here? Yeah, so you integrate, right? 2 gets cancelled out. So this is minus log of x is equal to log of y plus constant, right? Let's write that constant as log of c. So that means that xy, so this is xyc, right? So xy is equal to, or let's say this is minus. So this makes it x times y is equal to a constant. And why call that a constant at all? Actually, call that v, right? Because that's our other variable, right? The electric field lines represent v. If you start with u as your potential, then v becomes your field lines, right? That's the idea. So this is v over 2. That's nice. So what is our field line? So how do we look for v? These are, we can actually look at this electric potentials now. Once we have the idea of electric field from electrostatics, we know that we just have to draw perpendicular lines to the equipotential, right? Electric field is always perpendicular to the equipotential lines. But let's plot this itself. So y is equal to v over 2, 1 over x times v over 2, right? That's your constant. If v is equal to 0, what is it? Equal to 0. Equal to 0 is y equal to 0, right? Y equal to 0, so that's your y equal to 0. Y equal to 0 is this. If you want, how do we, so let me do it like this. So that's your v. That will be the second realization, but that's not a conductor yet. But this is the realization. That's the second realization. And 1 over x, these are all perpendicular, so it's very clear how this is going to go. So this is like this, and it does come out to be perpendicular. So basically, if you were to use these two as your plates, this forms your equipotential lines nowadays. It's kind of a exact conjugate, so that's why it's called conjugate. So if you were to use this as your quadrant, that forms your hyperbolas. So that should give you a feel of what it is. And in your homework, you're actually doing z cube. I think it is z cube and probably even higher, maybe z raised to 8, or I don't remember. Yeah, I remember the diagram, so I think you're doing z raised to 5 here. So you got to use a computer for this. There is one thing I can ask, where do you see these kind of electric field lines? So these are electric, so let me draw this again. Right? So electric field line seems to be like this. Correct? Or did I say this correct? It has to go from high V to low V, low U, right? High potential to low. So this is high U to low. So this was, yeah, this is correct. So this will be like this. Notice what will happen if you were to put a charge here. Right? Imagine what will happen to a charge if you were to drop it somewhere here. Along the x-axis, it is attractive. Right? It goes towards the origin in a sense. Right? Attractive in the sense that it is attractive towards the origin, but along the y-axis, it is repulsive. Those kind of scenarios are called saddle points, right? In one direction, you have equilibrium, the other point you have non-equilibrium. So that's called a saddle point. And have you guys ever, when you were kids, try to balance the north pole, one magnet on the other magnet? Right.
Yeah, sure.
Yeah, there's probably a good chance that at least thought about, oh, why can't we balance one, right? So you always try to, oh, maybe I can really make it work. And can you do that? Is it possible?
No.
Yeah, so it's as a stable point, it is always unstable. And that's called Earnshaw theorem. Have you heard of this?
Yes.
So Earnshaw theorem in electrostatics says that in static configurations, it is not possible to have charges in equilibrium. So if you have one charge here, another charge there, negative charge there, you cannot levitate one charge using static configuration of electric field. So yeah, that's an extra credit, let's say. So just look up Earnshaw theorem. So it's a good bit of information is there and a lot of thought-provoking points. But then, can you think of a system where actually things do levitate?
I think I mentioned to you I tried to think about a system of like using like a sphere.
Oh yeah, I'm talking to Jordan. Jordan has set up experiments on this, right? In acoustic scenarios. Yeah, I'm speaking to the wrong person. He's the expert here. So I think I don't know whether you guys are familiar or not. I think what Jordan did is that. Do you have that set up? Do you want to show them? Show them, Jordan. Do you think it will work in
I can.
2 minutes?
Yeah. Well, I can't do it right now because it's at a local high school at the moment.
Okay.
They're using it for their wave section, but as soon as I get it back, I'll.
Just why don't you say a few lines on what you did? Yeah.
I made what's called an acoustic levitator with little transducers, basically like little speakers that emit 40 kilohertz, and there's like an array, and each side has like a sphere shaped set of transducers, and they basically speak to each other and create a pseudo standing wave in between them. And you can take like little styrofoam balls and at all the places where the nodes are in the wave. So as you know, the waveform goes through, at all of those nodes, it creates what's called a trapping force. And you can take like styrofoam balls or water, and you can place it in those nodes, and it'll levitate. So I hooked it up to Arduino Nano and put a little program in there that allows you to move the standing wave, you know, from right to left with the speakers, and then you can levitate a series of like styrofoam balls or water and then move it left to right. It's kind of cool, but
Nice.
haven't really done much with it since I came back to school.
You can do it
This
with
challenge.
water droplets too.
Yeah, go ahead, Moses.
I said you can do it with water droplets too.
Yeah, you can do it with water droplets. Yeah.
That's pretty cool.
You can take like if you take something like a piece of paper and you place it at the node, you could spin it and it'll just spin like super fast. And if you can't hear it, but if you take your camera phone, because it's higher than our range of hearing. So when you look at it, you don't hear anything, but as soon as you try to record it on your phone, it'll start screeching. You'll hear, you know, and if you spin something really quickly in there, it sounds like a jet flying, but you can't hear it, you know. So it's kind of cool whenever you record it.
But similar challenges, so Jordan is doing it with acoustic waves. You can ask, you would like to trap an atom. Usually you want to study an atom, and the first thing you want to do is you want to trap an atom, and that's a whole field in itself.
Yeah, you can do
a big
lasers.
Yes, so but the big challenge that comes up is that often you will see naively is that, oh, Earnshaw theorem says that you cannot trap an atom because that would involve levitation, that's not stable, so forget it. Right, so this is the closest you can get. So this electric field lines is the closest you can get to having anything trapped, because electric field lines will come in one direction, but it'll always make a saddle point. But the key around it is that this is for statics. Earnshaw theorem is for statics. Whatever Jordan is doing is not static, it is dynamic. And you want to make it AC. Like you want to change the electric field in time. And then Earnshaw theorem, you get around Earnshaw theorem completely. So every time you look at Earnshaw theorem, or whatever says that Earnshaw theorem is getting violated, look for statics. Is this a static problem or not? And another, so there are two pieces that you should look for. One is that this is for statics. This is applicable to only for statics. And the second is that there are no boundaries. Right? By boundaries, I mean there are no dielectrics or conducting plate nearby. If there are conducting plates nearby, or if there is an extended form of charges you can keep, then all this can be violated. And there are nice toys you can see. Sometimes you will see a magnet floating on, like it is, so if I can show this. So if this is a wall, just a simple glass wall, and if this was a magnet, you will see that this is holding on to this, and there is another magnet here, and this will be just floating like this. Have you guys seen that guy? It's relatively popular.
No, basically the wall's preventing it from flipping.
Yes, so there is one magnet kept like this here. That's a flat magnet. And if this was a north-south magnet, but this is a glass wall, and it won't be able to go to the right-hand side. So that's a relatively standard one. Maybe I can try to show that. So again, when you look at this, and if you're aware of Earnshaw theorem, oh, this is a static scenario. What happened to Earnshaw theorem, right? And you wonder what is happening, and then you see that, oh, there's a wall there. And Earnshaw theorem did not keep a wall there. So wall kills that. So there's a lot of caveats in Earnshaw theorem. And in ion traps, this is very much used. So this is called a, so extra credit is, one is Earnshaw theorem, and the second is, I suggest, a Hall trap. This is what this is called, whatever the electric field lines that I have drawn. Notice that charges come here and they will run away on the other side, right? So what he did is that he basically made this AC, made this electric field flip from going from here to there and going from there to here. You flip between these two. So earlier the charges try to go that way, but before it can reach there, flip the electric field, so then it tries to come this way. Flip it again, it tries to go that way. So you basically trap it if the frequency of the flipping of the electric field is high enough, then you can actually trap it. So that's a cool idea that you can use. That's very closely related to what is called an inverted pendulum. Again, inverted pendulum is a pendulum, and typically pendulums fall like the stable point for the pendulum is just to hang this way, right? I think usually how you say is so this is a pendulum, correct? And this is vertically down. Now, is it possible for this to have a stability when it is pointing upward, right? Naively, no, right? I mean, it will fall away, it is unstable. But the point is, if you were to try this, if you were to oscillate this base in the vertical direction, not in the horizontal direction, horizontal direction doesn't work. If you oscillate it in the vertical direction with a frequency higher than, for example, for this height, it might be about 20 hertz. If you were to do this greater than 20 hertz, then even if you were to push it, it will come back on this side. So it has a stable point there. So it's called dynamical stability, right? So pretty cool. So it's the same idea as Paul trap. If you read about Paul trap, it will always mention inverted pendulum. But the idea is those are called differential, or actually historically speaking, where this comes in is that if there is a satellite going or moon going around Earth, in those days they were very much interested in astronomical orbits of astronomical objects, and the point was if there was an oscillation in the orbit of moon, then is it possible for it to disturb it? Like, can it get unstable because of that? If there were small oscillations, and what should be the oscillations be so that it can make it unstable? So those are studied in what is called Matthew functions. So these are all closely related topic, Matthew functions. That's a differential equation that describes it. Block functions, all those are related. It's there in all other everywhere, as probably Jordan has a lot more intuitive feel for all these things, but very hard to solve analytically, but has significant or very big applications associated with it. So if you're into research, you want to look into those kind of avenues where new things can come up. So that's all I will say there. That's an extracted problem. I mentioned it because these electric field lines came up. That's what is used in a Paul trap with AC field involved in that. Okay. With that, let me go to another topic. Actually, we want to do integrals. So analytic functions are good, but can we look at it? How do we do integrals, and how does analytic functions behave when you integrate it? So we have an analytic function f, analytic function f of z. It cannot depend on z star. That's the idea. And let's say this is defined on a complex plane. So it's a complex plane z. This is your x. That's your y. And now I want to integrate from on a straight line. Integration is simple. But if I want to now integrate on this plane, you will integrate on a line, so on a curve actually. So this is z1 and that's z2. And that's not well defined enough. I have to specify the curve properly. Right? So this is so often we call it contour. So for now, let me say path. So the path in this context is called a contour, often represented by the letter C. So that's a contour, and we want to see how does it matter, right? So we want to do integral of dz going from z1 to z2, and I have to specify the contour, which is, let me at this point say this is path of f of z. Right, that's what we want to look for. Let's see what dz and f of z is. Notice z is equal to x plus iy, and the function, analytic function is u plus iv. U is a function of x and y. U plus iv. So dz is dx plus idy, a small tiny differential element associated with it. So what is this integral about? So this is nothing but z1 to z2, where z1 and z2 means x1, y1, right? If you're thinking of it in a two-dimensional plane, this is specified by x1, y1. So let me write that more specifically. So I'm going from x1, y1 to x2, y2 along a path, right? Along a specified path, and dz is dx plus idy, and f of z is u plus iv. There are 4 terms in this. Okay, so let me write those 4 terms. So this is z1, z2, out, and dxu, this is dx times u, right? Dx times u minus of dy times v. So that's your real piece in there. Let me write this. And there is a complex piece, so that's plus I times dxv and plus dyu. Okay. And that's what we want to evaluate. Each of this is a dx times some function times dy times some function. So let's do it some arbitrary. So let's do the following. I would like to do the following integral. I'm again going from x1, y1 to x2, y2 along a, so this is dx, and p as a function of x and y. P is some arbitrary function. P can be u, p can be v, p can be v, p can be u, some arbitrary p and xy, so making it very general, and plus dy times q of x comma y. So I would like to know, how do you integrate this? Right, along and actually, let's also not just do from x1 to y1. Actually, I want to do a closed integral. Okay, so that means to say I go from x1 to Z1 to Z2 along one path and come back along another path, and I want to see what it is, and I'm going to show that actually this is equal to 0 under some situations, under some conditions, this is actually equal to 0. Okay, under what conditions is it 0? By the way, if you use the ideas of conservative force, right? Conservative force involves when the work done is 0, is path independent, correct? Then that comes out to be 0, which means that del cross of the cross product of the force has to be equal to 0. And we did emphasize early that a complex function can be thought of as a dot product and a cross product, but let's just do this from an elementary way. Under what conditions is this equal to, is path is equal to 0? Okay. So let's actually make a small path instead of making a big path. So once you do it for any arbitrary path, you can actually always prove this. Let's say this is my xy point, and I go from, this is my closed path. I start from xy and go to x plus dx and keep the y the same. Then I keep x plus dx the same and increase y, and then come back here. This is x again, but it is y plus dy. Right. So this involves 4 contours, right? So there's 4 pieces on one of them, 4 pieces on the other one, if you want. So let's do. So this is C1, this is C2, this is C3, so that's C4. On the contour C1, my dx is finite, but dy is 0. Right? So it is, I would say, dx times value of the function. I can evaluate it at this point or the other point, because we are taking only the leading order. Right? This is a calculus. It's not actually an approximation. In the limit, it perfectly works out. So this is equal to dx times e of xy. And dy is 0, so I don't have to worry. Okay, that's right. On C2, on contour C2, change in x is 0, but I have a change in y, so this is 0 plus dy times, but now I have to evaluate this at this point, right? I can either evaluate it at this point or this point. So this is q of x plus dx. Oh. So evaluating at this point. First one I evaluated at this point, second one at this point with the line element there. And C3, same thing. Now it is minus dx. So this is minus dx. And I have to evaluate it at this point, but this time I would choose to evaluate it then. So this is p of x comma y plus dy. And dy stays the same, so it's 0. And C4 is equal to minus dy, so that's 0 minus dy, and evaluated at at q of xy. Right. My integral, so let me call this I, right? It's my integral, loop integral if you want, closed loop integral is dx minus dx actually. So this is minus dx times p of x comma y plus dy minus of p of xy. And this one is minus plus dy q of x plus dx comma y is still minus q of x comma and these are integrals if you want. This is an integral and this is an integral. But this one can be expanded. When I expand, this leading order cancels out. And what I have is the x times dy of, let me write the q function first. This is dq by dx. And here it is negative. This is dp by dy. And if you want, this is a small loop, so you can think of this as an integral of that small loop. But now notice, what if this was 0? This is equal to 0 if, or let me just not say anything. This is what the loop integral is, right? At this point, if it is 0, then it is actually independent of the path. That's what we would say. But now let's do the same thing in here. How do we use that? So that's our integral. Here, if I were to do this as a closed contour integral of dz f of z, that's equal to as a dx and dy if you want, x dy. This is, by the way, this proof here is nothing but, what is this, by the way? Any thoughts? What is it similar to? Have you seen it somewhere else? You guys are muted if you guys are saying anything, but maybe not. This is nothing but Stokes' theorem, right? This is how Stokes' theorem is proved, if you remember your vector calculus. This is exactly Stokes' theorem, right? A line integral becomes an area integral, right? Right. This is called Stokes' theorem, Green's theorem, various ways, but I think it was Stokes who did it for the first time. So, in this case, we have, there are two integrals now. In this case, u is p and q is minus v. So, q, so this is minus v, so this is dv by dx, and this is minus du by dy. And plus I times v plus u. So v is p. So this is dq. So this is du by dx minus of dv by dy. what are these equal to? What is this equal to for an analytic function?
Zero.
0, and that's because Cauchy Riemann conditions, right? So that's equal to 0. In fact, this is also equal to 0. That's the other Cauchy Riemann condition. That's equal to 0. So for an analytic function, the contour integral is equal to 0. This is exactly like our divergence theorem we were doing, right? Except at one point, if there is a delta function shows up, then it's a problem. Otherwise, it's 0 everywhere, whichever loop you do. So this is exactly the same thing. So this is Cauchy's theorem. Just with this, you can do everything in complex. So that's what Cauchy almost finished the complex analysis. That's kind of a popular statement he did. He hardly left anything, simple things left for others to work on. And we will exploit this. So now, for example, if you understand what this contour integral is, another way of exploring analytic function is, given an analytic function, you make all these arbitrary loops, right? Independent of what loop you consider, it should always be 0 if it is an analytic function. So that's one way of looking at it. And we will come back and do a lot of examples on this. At this point, let me not begin. It's 10 minutes early for a change. Any comments you guys want to make since we have 10 minutes? I don't want to start another example. Like I can do an example and do this, but yeah, let's stop. It's kind of in a nice place because very soon I would like to do in electromagnetism. I'll be doing Kramer's chronic relations, which will be actually using these integrals. So since many of you are there, that actually all of you guys are there, right? Yeah. So it should be useful. That's all. Thank you.
Okay, thank you.
I have a small question about the course.
Sure. For the
Just
course.
So,
Yes.
yeah, so if we don't have class on Monday or Tuesday, are you not having office hours Monday and Tuesday as well?
Oh,
Is
good
that
point.
connected?
I can have office hours actually. I can have
Okay.
office hours. Yeah.
Okay.
So I will have office hours on both days.
Okay.
Yep, that's good. So I'll be around here. I'll be in Carbon. Okay, good. And you're all welcome to use the office hours. There are some undergraduate students who show up, but I mean, if you wait for a few minutes, usually one student doesn't take too long, and most of the time I'm open. So I'll encourage you guys to come down. Or maybe actually we can also do, actually, now that the cases have gone down, we can, if you're around, you can also come to my office. Okay? So if you feel more comfortable that way. I shut it down because I felt I was putting others into more uncomfortable situation. I felt in the department, no one else was having it, and I was having so many students come over. My office was always having students. So I felt I was putting people in the wrong. So that's why I switched up. But now I think we are better off, and I can also expect that the graduate students mostly are more responsible, I think. So you're welcome to come to office hours, but I'm not encouraging you guys, if you feel like Zoom works, if you're comfortable with Zoom, do that. I think there are many people I notice that they are still uncomfortable about moving around, which it should be. I mean, I'm saying that should be respected. Like even I don't move around too much, but I'm ready for the office hours to be open. That's all. But if everyone starts thinking like me, suddenly the cases will go up very high. Right, so you don't want to do that too much. So that's what Luke said. What was it? Collective bargaining, right? Yeah, you don't want to let that happen. Yeah. So a little bit is here and there is okay. Yeah. Okay. But Zoom works, I've noticed. So use Zoom. Yeah. Even for office. Yeah. But you're welcome if you want to. So yeah, Monday, Tuesday, I'll be around. Everything is there. I just don't want to have classes on that.
Sounds good.
Mm-hmm. And maybe I don't think we are slowing down. I do want to do complex analysis in this detail. Usually you don't get to see this so much. It's a good thing, I suppose. And what we will lose a little bit is partial differential equation, which still I will do reasonably well in the sense I'll use Green's function methods. So hopefully that will be useful again. So what I'll skip is in partial differential equation, there are two things. One is homogeneous differential equation and one is inhomogeneous. Homogeneous is what most of the time we do, but I will assume that those solutions are known and directly go into inhomogeneous. But most of you probably have seen partial differential equation, homogeneous differential equation somewhere or the other. And I'll do a little bit. It's not that I won't do anything. I'll motivate it enough. So hopefully all that will fall in place. Okay. And don't get disheartened with the grades. This is just the first. I do realize that I think maybe there's a lot of it on my end also. So keep pushing on it. It doesn't mean anything. There's a lot of exams, a lot of grades that will override it. So. Good. That's all.
Thank you.
Mm-hmm.
Thank you.
Yeah, bye-bye.
Thanks.
Mm-hmm.